friends, in the last session we had a look at the different shapes that molecules can have, and we said, just very basically, just to recap, we said that the covalent compounds can be divided up into specific shapes depending on how many bonding pairs of electrons and how many lone pairs there are on the center atom. We then said that single pair repulsion is the strongest, bonding pair is the weakest. All right. And we found then that molecules can be pushed into specific shapes. Carbon dioxide forms a straight line. We say that molecule is linear. All right. Most of the covalent compounds that consist of two atoms will be linear. Then we said water. Can anyone remember the angle that there was between the hydrogen, oxygen, hydrogen on the water? I think it was 107 or 104.5. Okay, we'll have a look at them in a moment. But we said then the water molecule is V-shaped. Ammonia, NH3, is pyramidal, and methane is tetrahedral. Now we are going to have a look at them as we do in theory. Okay. Now, what is important is that carbon forms the center atom. We have two bonding pairs there, two bonding pairs there, two single pairs. We will find that the repulsion on both sides of the center atom is the same. All right, and it will push the angle between the oxygen, carbon, oxygen into a straight line there. All right. So the repulsion of the oxygen atoms is the same. Therefore, the bond angle is 180 degrees, forming a linear shape. Very important, the name of the shape. Then from that, we can go and have a look at the water. We see here that the oxygen has got two single pairs which repel each other strongly in 3 dimensions, as far away as possible. Then we have a bonding pair over here, bonding pair. So the repulsion between bonding pairs and single pairs is also fairly strong, but not as strong as between the single pairs only. So that also pushes the hydrogen atoms away downwards to one side. The repulsion between this bonding pair and that bonding pair is very weak, so they can't repel each other very strongly. And as a result of that, we find that the bond angle over here is going to be 104.5 degrees. Now you need to remember the size of the angle. Okay, they won't ask you obscure examples, but you need to know carbon dioxide, water, ammonia, and methane. All right, it's just basic classical, or the classic examples for V-shaped, pyramidal, tetrahedral. Okay, so water then is 104.5 degrees, the bond angle. The next molecule that we have to have a look at is the ammonia molecule. Remember, it's NH3. So in the ammonia molecule, we have got 3 bonding pairs that repel each other fairly weakly. All right? So the repulsion over here and over there is not very strong. And, well, over there, remember, it's 3-dimensional. It's not very strong. We only have one single pair over here. So we don't have single pair repulsion like we had in water. All right? We've only got single pair, bonding pair repulsion, and bonding pair. That is why we find that the bond angle in the ammonia molecule over there, that angle, is slightly bigger than in water, because the forces pushing those hydrogens down to one side are slightly weaker. So the angle over here is 107 degrees. Same over there as well, 107 degrees. All right. Okay. The last one, we call the shape then of the ammonia molecule, where we have a single atom over here and 3 on the bottom, forming a triangular base. We call that triangular pyramidal or just pyramidal. All right. There we go. Is a pyramidal shape. Then methane is probably the easiest one to explain of the lot. Are there any single pairs of electrons? No. We have 4 sets of bonding pairs. There's one set, there's another set, and another set. And we find now that the repulsion between these pairs are fairly weak, but it is the same in 3 dimensions. There's not a force pushing it stronger from one side of that molecule. So these carbon-hydrogen, the hydrogen-carbon-hydrogen angles will all be the same size, and they will be as far away as possible that they can get in 3 dimensions, forming an angle of 109.5. So, try and remember it. Water, 104.5. What was ammonia? 107. And the last one that we've done now, 109.5. So 4, 5, 6, 7, 8, 9. Okay. Try and get yourself a system to remember the size of the bond angle. If you can remember the sizes, you would be able to figure out which size belongs to which atom. Why is the bond angle in water smaller than in methane or ammonia? Because in water, we have got single pair repulsion that pushes the hydrogen atoms down. You follow? All right. Why is the angle in ammonia bigger than the angle in methane? Methane only has bonding pairs which repel each other equally weak in all directions, while in the ammonia molecule there is one single pair that repels the bonding pairs fairly strongly away. All right. So you need to try and remember the size of the bond angle. Okay, people, now we've had a look at ionic bonding. We've had a look at covalent bonding. Now we're going to compare the properties of ionic compounds and covalent compounds. Now the physical properties of these compounds have got to do with the strength of the forces between the particles. What makes it sometimes difficult to understand, if we have an ionic compound, we have a crystal lattice that consists of positive and negative particles, and you can all understand that opposite charges attract. So we said then that in an ionic compound, the forces over here between the particles, what are the particles? Ions. What forces do we have between ions? Are Coulomb forces. Okay, the Coulomb forces are fairly strong. All right. Now, when we're going to have a look at molecules, it's slightly different. A water molecule, for argument's sake, will have that shape. So here is the whole water molecule. Within the molecule over there, we have a covalent bond. It's a chemical bond. But if I have 2 water molecules, what forces exist there? Those are weak. Van der Waals forces. All right. Between molecules, we have weak forces. Between ions, we have the ionic bond. It's a chemical bond. It's strong. Alright, no matter how big my salt crystal is, whether I have one as big as a grain of sand, or I have one as big as a block that I go and put out for the cruise to lick near the water, okay? The salt crystal is held together by ionic forces, electrostatic forces between ions. It's a strong chemical bond. But with molecules, we differentiate. We talk about intermolecular between two molecules. The inter-Cape bus travels between Cape Town and Windhoek, the inter-Cape. But within the molecule over there, those forces there, let's do them in a different color. Those forces, that is an intramolecular force. It's a force inside the molecule, and that happens to be a covalent bond, which is strong. Covalent bonds are strong like any other chemical bond is strong. But I think what confuses you eventually is the fact that when we work with ions, it's easy to understand. The forces between the particles are just Coulomb forces, forces between charged particles. But when we start working with molecules, we have to differentiate two types of forces. The chemical bond within the molecule. And that one does not determine melting and boiling point. Okay? The forces between the molecules are the ones that determine melting and boiling. You need to understand this concept very clearly. My fingers are bonded onto my hand. Okay? I can't break off a finger very easy. That's like the forces inside the molecule. But my two hands can be held together by weak van der Waals forces. Alright, it's an image. Okay, so it's not within the molecule. It's between the molecules. Alright, and from that we can differentiate specific physical properties. People, ionic compounds, we've done this in previous years. What are the properties of ionic compounds? They are all solids and they are all hard and brittle. So if you hit them with a hammer, they will shatter. Alright, why are they hard and brittle? We have strong forces between the particles. If there are strong forces between the particles and I want to try and make that solid melt, I'm going to need lots of energy to give the particles enough energy to vibrate far away from each other to overcome the forces. So we find then that ionic compounds have high melting and boiling points. People, they are really high, 900 degrees, 950, 2015 degrees. Okay? They have very high melting and boiling points. The reason being strong electrostatic or Coulomb forces between the particles. Ionic compounds, they can conduct electricity, but not in the solid state. Because why? In the solid state, the charged particles are held fixed in a crystal lattice. Alright, to be able to conduct electricity, the charges must be able to move. So when I melt a salt, or when I dissolve a salt in water or any other liquid that it dissolves in, we will find then it will conduct. Alright. The reason why water conducts electricity, the water coming out of the tap, is there are salts dissolved in the water. So it's actually not the water that conducts, it is the dissolved salts that are the charges that can move. And the moment you have moving charge, you've got electricity, current. No? Pure water won't conduct, it's molecular. Alright, so it will conduct in the melted or dissolved state, and it's important to state that. Okay, because later on when we do the metallic bond, metals will conduct whether they are melted or whether they are solid. Okay, so you must distinguish. They will conduct when the salt is melted or dissolved. It does not conduct when it's in the solid state, because the charged particles are held in a crystal lattice. Okay. Covalent compounds. Remember, the forces between the particles are weak. So, if they are solids, they will be soft. Mothballs, for example, are molecular solids. What happens to mothballs if I leave them on the shelf, open outside of the packet? Doesn't dissolve? What's the process called? Doesn't evaporate? Yes, it undergoes sublimation. It goes from the solid state directly to the gaseous state. Why doesn't it go to the liquid state? The forces holding those particles together are so weak. At the moment the particles get enough energy, they can go and become a gas. All right. So, if they are solids, they are soft solids. Usually we will find that any of the covalent compounds that we work with are liquids, or, there's a typing error, or gases. People, if we look at things like HCl, HCl is actually a gas. We work with it as hydrochloric acid, but that's the gas dissolved in water. That is why when I open up the bottle of HCl, it immediately starts giving off fumes. Ammonia is another one. NH3 is actually a gas at room temperature. It dissolves in water. So I can add it to Handy Andy to help clean up fatty deposits, etc. But when you work with Handy Andy, you immediately smell the ammonia because it wants to become a gas again. Things like hydrogen sulfide is a gas. Carbon dioxide, CO2. The only one I think that you really work with that is a liquid, or not even work with, but that you know of, is bromine, diatomic molecule. It's a liquid. Iodine is a solid. But iodine, just like mothballs, if I have a crystal of iodine and I start heating it, it doesn't melt, it immediately becomes the gas. Alright, so the forces between those particles are very weak. That is why most of them are in the form of a gas. The ones that are liquid would be my organic compounds, because the molecule gets a little bit bigger and a little bit heavier. Okay, and then they require a little bit more energy to make them evaporate. So things like ethanol is a liquid, methanol is a liquid. Okay, carboxylic acid is a liquid. Okay, those ones then, but we won't work with them at this point. When we do organic chemistry, we will work with those ones. All right, so they, because of the weak forces, they will have low melting and boiling points. You understand that? Requires very little energy to be added so that the particles can overcome the attractive forces. They use the term low volatility. In other words, they will evaporate very easily. Okay. Low boiling point goes together with low volatility. It simply means it will evaporate very easily. For example, if I have diesel in a puddle and I've got petrol in a puddle, the diesel is going to take longer to evaporate than the petrol. Okay. Petrol is more volatile than the diesel. They do not conduct electricity. Okay. Why don't they conduct electricity? What is electricity? Current. Moving? Charge. Are there any charges that can move? No. All right. So there are no charged particles, so it cannot conduct electricity. And the last one, mostly not soluble in water, while the ionic compounds are mostly soluble in water. Now this last one, there are quite a few exceptions to the rule. In general, in chemistry, we say, like dissolves like. Something will dissolve another substance if the forces between the particles are more or less the same size. Does that make sense? Because if the forces between, let's say I've got a liquid, and the forces between the liquid particles are very strong, and I'm trying to make a solid substance dissolve in it, if the forces between the solid substance is not strong as well, they can't move in between each other. Alright, so like dissolves like, there are a couple of exceptions. Normally, for example, if I take sugar and salt, if I take petrol Petrol is a molecular substance. It's a hydrocarbon. Sugar is also a hydrocarbon. Sugar can dissolve in petrol. If I took normal table salt is ionic. Table salt does not dissolve in petrol. Why? The forces between the salt particles are much stronger than the forces between the petrol particles. Do you understand that? Now, water messes us around. Water is actually a very, very special compound, and you've done that last year already where we said we look at the melting point of ice and what happens to, why does ice float on water? Because it expands between 4 and 0 degrees. Okay, now water, because of its very special shape that it has, and because of the 2 single pairs of electrons that don't form a bond, we find that the water molecules, the forces between them, the water molecule is almost, it isn't an ion, but it's almost an ion. Okay, it's got a slightly negative side and a slightly positive side. We'll have a look at that later on as well. So we find that water can sometimes dissolve molecular substances, and other times it can dissolve ionic substances. For example, if I add water to petrol, will they dissolve? No. But if I add sugar to water, will it dissolve? Yes. You understand? Okay, so there are many exceptions, but just as a general rule, like dissolves like. Right. Okay, so those then are the properties of ionic compounds and covalent, just very general properties. Now, the next term that we have to have a look at is something called an allotrope. Nice new definition. Have you done allotropes before? Nope, you've not. So allotropes, they are different crystalline structures for the same element. And a very, very well-known example is diamond and graphite. They are both made out of carbon. But we get 2 different crystalline forms. They are formed under different conditions. Diamonds are formed under very high pressure and very high temperatures. All right? Usually in the columns of volcanoes with a molten rock and organic matter that is burning, all right, and sublimating. When it cools down and there's no oxygen present, then we can get the formation of diamonds. Graphite is formed under different conditions. Graphite is the stuff they put in your pencil lead. If you have a lock that sticks, you buy graphite powder and you puff a little bit of graphite powder into the lock. It acts as a lubricant. Okay? Both are made out of carbon. Now, we will go into the specific shapes of diamond and graphite in one of the next units. Right? So, there's a third allotrope for carbon, one that is called Buckminster Fullerene, or just very simply shortened down to Bucky balls. Okay. The Buckminster Fullerene consists of 60 carbons covalently bonded onto each other in structures that look like a soccer ball. You follow? The patches on a soccer ball? Okay, 8-sided. Buckminster Fullerene look like a soccer ball. So it's a hollow ball of carbon. All right. We will go and look at materials that are made with them and things in one of the next topics. I don't want to start with that now. Just a little bit more about Buckminster Fullerene, or just Bucky. They will accept both. It shouldn't be a problem. They sometimes refer to them as fullerenes as well. They are homonuclear. What does that mean? Homonuclear. The same nucleus. What is heteronuclear? Different nuclei. In other words, bromine is homonuclear, diatomic, same bromine and bromine. But HCl is heteronuclear, a hydrogen and a chlorine. Okay, so Buckminster Fullerene are homonuclear because they consist of carbon atoms, identical carbon atoms. They can be spherical, okay? That's their natural form, the buckyballs. And we can open them up and we can build them into structures like tubes, which we will go and have a look when we do different materials. And this is where we get the carbon fiber materials, etc., that are very strong, and so on. The spherical fullerene contains 60 carbons and are called Buckminster Fullerene, or buckyballs, while the tube fullerenes are known as nanotubes. Where have you heard about nanotubes? They're investigating nanotubes in terms of conductivity, because graphite conducts, and the nanotubes are made from the fullerene, that they tend to, well, make them build onto each other to form long tubes. And these tubes can conduct electricity. There is less resistance in a nanotube than there is in a copper wire. All right, so in terms of, yes, at this point it is expensive. All right, but it's where the new research is going into. Okay, fullerenes are used as drug delivery systems to the body, lubricants, and catalysts. Now we'll have a look at that when we get there at this point. There's a check your progress, page 135, that you have to do for me for homework. All right?
On GoTV, you know what you want. You want superstars.
What about that?
The biggest names in the game. And of course, the best leagues in the world. Yes, you want explosive football action. And this new football season, we're serving it to you on a shiny new platter with our revamped Super Sport channels. All you have to do is tune in and we'll make it worth it. So get and stay connected to GoTV for football worth watching. GoTV, live it, love it.
Akili, 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 Akili. We love to wash our hands, and this is how we do it. Wash, wash with clean water. Scrub, scrub, scrub with soap. Rinse, rinse with clean water, and then the germs will go. We love to wash our hands, and this is how we do it. Wash, wash with clean water. Scrub, scrub, scrub with soap. Rinse, rinse with clean water, and then the germs will go. Yay! Well done, soap and water. You got rid of all the germs on Achilles' hands.
Win a share of 20,000 Namibian dollars. SMS the word VIBE to 10010 and stand a chance to win 2,000 Namibian dollars with the Ink Like a Vibe show. Watch the show on One Africa TV, channel 284 on DSTV, and channel 90 on GoTV.